Hello, here's the key for the 8.8 to 8.10 quiz. So we have 8 multiple choice questions on this one. All right, so with question number 1, we have a buffer system, and we have this is the weak acid right here, the HC2H3O2, and the conjugate base is going to be the C2H3O2 ion. The sodium right here is just a spectator. All right, so we have the solution. We say the pH measured to be 4.73. And you add hydrochloric acid and the pH remains at 4.73, so we don't get a significant change. So I want to say which of the following equation represents the chemical reaction that accounts for the fact that acid was added but there was no detectable change in pH. So what happened to the buffer system when this hydrochloric acid was added? Well, when you add hydrochloric acid, really the only thing, the chloride is just a spectator. That's not doing anything. It's the hydrogen ions. And then that's represented down here with the hydronium, H3O+. So the hydronium is going to react with the conjugate base and is going to produce HA or acid molecules. That's the direction. It would be a shift left from the way we wrote it out of the notes. When we add hydrogen ions, it causes the buffer system to shift left so that hydrogen ions don't build up, but instead we create these acid molecules. So the conjugate base is the C2H3O2, so we want to react that with the hydronium ions and it produces these acid molecules, so it's going to be letter C. Question 2, which one would be considered a buffer? So a buffer is going to be a weak acid with its conjugate base. HCl is a strong acid, HBr is a strong acid, so that eliminates those. So choice 2 right here is the only option, so that's going to be letter B. All right, question 3, we see a titration curve. And at the equivalence point, it's above where point X would be. It's above 7, so we know this is a weak acid conjugated, or not conjugated, titrated with a strong base. So a weak acid and a strong base titration. So which part of the curve corresponds to the optimum buffer action for this acetic acid acetate ion pair? This area down here is called the buffer region, where you have some of the weak acid and some of the conjugate base. Now at the half equivalence point, that's where you have equal amounts of each of those, and that's the optimal buffer region for this right here, for this acid. So it's going to be the half equivalence point is where you have this optimum buffer action. So that's where it can handle the most amount of acid or the most amount of base that's going to be added. So it's going to be point V. So letter A. Question number 4. All right, so we have the same acetate buffer solution. So you have this acetic acid and you have the sodium acetate. So again, the sodium is just a spectator. It's just the acetate ion. That's the conjugate base. All right, so we start off, we have the pKa of acetic acid is 4.7. So if you have equal amounts, like what we do here, we have 50 milliliters of 0.2 molar acetic acid and 50 milliliters of 0.2 molar sodium acetate. So we're starting off with equal amounts of weak acid and conjugate base. That means that the pH of that buffer is going to be the same as a pKa. So we're starting off at 4.7. All right, now it says we're adding 5 milliliters of base. So the base will combine with the hydrogen ions in the buffer reaction, and it eliminates the hydrogen ions and it causes a shift to the right towards the conjugate base. So after we add the sodium hydroxide, it'll shift towards the conjugate base. So that's going to have the highest concentration. So that eliminates A and B. And then since we're causing a shift to the right, we're going to have more of the conjugate base than we do of the weak acid. So that's going to drive the pH up a little bit. So it's going to be slightly greater than 4.7. So we have more of the acetate ion or conjugate base, and it's going to make the pH just a little bit greater than 4.7. If you have equal amounts of conjugate base and acid, then the pH is equal to the pKa. If you have more of the weak acid, then it's going to be less than that, the pH is going to be less than that. If you have more of the conjugate base, then the pH is going to be more than that. All right, question number 5. So we have different values of Kas for these 4 different weak acids. So which of the following pairs of chemical species, when combined in equal molar amounts, results in a buffer with a pH close to 7.5? All right, so this is the Henderson-Hasselback equation. So we want the pH or the pKa to be closest to the target pH. So the pKa is going to be the negative log of these Ka values. Well, the one that gets you close to 7.5 is going to be this 3.0 times 10 to the negative 8th. The negative log of this value, I think it was 7.52. So that means this is going to be our weak acid, and we want to combine that with equal amounts of the conjugate base. So the conjugate base is going to be the ClO -1 ion. So that's going to be letter C right there. So we want the pKa equal to the pH to make a buffer system close to some target pH. All right, on the basis of the information above, a buffer with a pH of 9 can best be made by using which of these? So these are all considered weak acids. We want again the pKa to be closest to our target pH. So the one that gets us closest is the negative log of this 8 times 10 to the negative 8th. It's a little bit more than 7, but then you can tweak the pH by changing the ratio of conjugate base to weak acid. So you'd want to have this as your weak acid. So H2PO4, and you combine that with the conjugate base of that. So that's going to be letter D right there. Okay, so we have this chemical reaction up here. So we have a pKa of 4.8, which is the best estimate for the pH of a buffer prepared by mixing 100 milliliters of 0.2 molar of the acid and 100 milliliters of 0.1 molar for this. This is the conjugate base right here. So this is our weak acid right here, and this is our conjugate base. All right, now we have 100 milliliters of 0.2 molar HClO4 or HC4H7O2, and we have 100 milliliters of 0.1 of this conjugate base. So we have a higher amount of this weak acid. So that's going to make the pH of the resulting solution slightly less than the pKa. We have more acid than we do of the conjugate base, so it brings our pH down to a lower value than the pKa. So it's going to be something less than 4.8. So we would pick B, 4.5. All right, we have another titration curve. So we have 50 milliliter sample of acid HA of unknown molarity is titrated, and the pH of the resulting solution is measured with a pH meter and graphed as a function of the volume of 0.1 molar NaOH added. So this is another weak acid, strong base situation. You can tell because the equivalence point, which would be right about here, is above 7. So at which point on the titration curve is A negative, the conjugate base closest to twice that of HA? All right, now at the start of the titration, like point Q right here, you have only HA. At the equivalence point, it's all been turned into the conjugate base, A negative. At the half equivalence point, which would be point S, you have equal amounts of those. So HA would be equal to A negative. As we progress to the right, the concentration of the conjugate base goes up and the concentration of the weak acid goes down. So we would say point T is where we have the conjugate base about twice that of the weak acid. So it has to be in this region right here, and point T is the only point in that region. So it's going to be letter C. And that's all for that quiz. All right, have a good day.